Hello, welcome back to 14 Minesweeper variants. Well, I guess you've guessed it, we're gonna do more 8x8 plus, now with bridge and deviation, yeah, the thing that I dreaded last episode. Okay, so, bridges. So, for bridges, you will have 3 chains of mines going from left to right, because yeah, 2 chains for a ball of 7x7 or larger. This chain will be a group of mines from this side to this side that can only move diagonally or horizontally, so you can only make forward progress. You're not allowed to make vertical progress or end your chain before reaching the end or break off this chain like that. That's how a bridge works. Deviation means numbers just refer to the 3x3 above it as opposed to the 3x3 around it. Not that hard to understand. So yeah, the 5 looks at those 8 cells, the 2 looks at those 8 cells, which is pretty intriguing. For some, yeah. So for example, this now can't be a mine. If it were, a property of bridge is that every mine must have something before it and something after it. If you think about it, the bridge variant is a bit like taking each column to be a single slice and having your 3 mines in each slice move up and down from one slice to the next. So this mine, for example, in the next slice we have to either move up or move down or not move at all. And the same for the one before that. It must have come from something that's above it, below it, or at the same level as it. And therefore, one way you could think about this is that if a mine was here, you'd have to have at least one mine here and at least one mine here. That breaks this value, which is now no longer a 2. So this can't be a mine. Now 1, for same reason, can't have a mine here. It also can't have a mine here, because that will force a mine up here. And for the exact same reason, can't have a mine here, because it will force a mine there. Now this can't be a mine, because if it were, where would it come from? It can't come from here or here. And so this one is actually, well, this 2 and this 1, we're not sure. This can't be a mine though. If it were a mine, it can't actually move forward at all. So the 2 is actually complete. These are both mines. And this mine must come from somewhere, which has to be here. So the mine comes from there. This now can't be a mine. This mine must now go forward here, which means this happens. Now this can't be a mine, because it can't move anywhere. Give you that. 1, 3 implies that there's 1 mine here and 2 mines there by subtraction. Not sure how that might be useful. This 3 is interesting though. Right, okay, so let's say for this 1 over here, the mine was there. That fails. Why? Because these 2 will be empty. You have to have mines here, here, and here. And where would this mine go? It doesn't have anywhere to go. So you can't have your mine be here. Your mine has to be in one of these 2 cells, and then there will have to be 2 mines in these 3 cells. Yeah. Okay, as for the 4-3 combination, well, the 4-3 combination does help, because if we compare this area with this area, which is what the 3 and 4 differ by, you see, this area must have 1 more than this area, right? So this area must have 1 more. Now what does that mean? If it has 1 more, it's either a 2-1 or a 1-0. Right? And I'm wondering if it's possible for it to be a 1-0. I think the answer is no. Because if it were a 1-0, then for this one, you must have a mine there. But where does it go now? Backwards. Can't come from there or there. So it actually can't be a 1-0. I'm pretty sure it's a 2-1, which means that there are 2 mines here. And as a result, 1 mine here. Cool. And because of that, there are exactly 2 mines in here. Yes, okay, well, an implication of bridge, which I've said a lot of times before, is that because you consider each slice to be a segment, a piece of like a slice of mines, each slice must have an equal number of mines. There are 24 mines total, and the 8 slices implies that in total, every column has 3 mines. You can also get that from the fact that there are 3 bridges, so naturally there will be 3 mines total. If you take a look at these 2 mines over here, they can only have 1 mine at maximum because column G already has 1 mine here and 1 mine there. And so, it can't have both mines in it. So this can't be empty. which means that this has to have a mine, which means that's empty, because now column H has 3 mines total. Because there's 1 mine over here, which we know, that is where this mine has to come from, right? And I think I'll use a different color here, maybe green, to indicate the bridges. This we now know connects to here. We also know that because there's a 3rd mine in here for the column, this can't be a mine. Cool. And 0 means that's not mine either. That's not a mine either. That's not a mine either. Wow. Okay, well that's sort of useful. I guess for column F now, there is 1 mine in here and 1 mine here. That makes 2 mines, so there must be a 3rd mine here, which must come from here, I think, because nothing else can come to here. Sweet. Right. How is this useful? How does that help? How can we do anything from here? Not sure. I guess it's somewhat interesting that, yes, this mine, this bridge, where does it have to go? Where does it have to come from? It has to come from either this cell or this cell. So there's 1 mine in here. And that actually completes column E, because there's 2 mines here and 1 mine here. That makes 3 mines total. So column E has 3 mines, meaning that these are both non-mines. Cool. Now this mine has to come from here for its bridge. So that extends its bridge this way. And now 3 implies that there is a total of 1 mine in these 3 cells. That is useful because this mine has to come from one of these 3 cells, right? And so that will complete 3, meaning that's not a mine, and therefore for the 2 mines here, that is. Okay. This is probably coming from the 2nd bridge, the middle one. But we don't know where it proceeds to. It could be anywhere. So it could look something like this, or it could look something like this, and we don't know. I'm pretty sure we do know that they're alternating though. Yeah. Okay. However, we do know that the bottom mine, the bottom bridge, can only take up these cells at maximum. So it can't go any lower than that, because the bottom bridge already takes up these 3. These 3 are the lowest possible cells for the mine to be. So there can't be a mine there. 1, 3 is very simple. Oh no, it's not, because it's deviation. Yeah, 3 is not because it's deviation. If it were regular 3, then these 3 would just be mines. It also looked like it would also not be possible. But 3, we're now looking at these 5 cells. Okay, well, there can be 2 cells here at maximum. And if there were 3, I think that might be a problem. If all 3 were cells, if all 3 of these were mines, then I suppose you could have a mine here that bridges this way. But where does this go? This can't bridge to this mine, which is a 2nd middle bridge. Because yeah, that's just not enough space. So that isn't possible, I think. Which means that there must be at least 1 mine in here. And that will be the mine that takes up these 3 cells. So there can't be a mine there. 1 mine here. And as a result, 2 mines over here. Now, as we know, one of the mines will have to take the bottom bridge. The other mine has to take the middle bridge. But how would that be possible? In fact, how would that be possible? Oh, no, it's not. There's only 1 here, because there's already a mine here seen by this 3. I see. And that would have to be for the middle bridge. Okay. Now I think the same works for this 3, where there has to be a mine here and a mine there. Because of this mine. Which has to come out here first, we know that, for this mine. And so I guess for column D we can already say there's a mine there. We can also say that wherever this mine is, has to take up one of these 3 cells. Why? It can't take up this cell because that would then force this one to go down this way. So in effect, it basically just says this and this. Either that or it just takes up one of these cells. So there is exactly 1 mine here. And as a result, this has to be a mine. For the 3, there's 3 mines here already, so that's empty, that's a mine. This 3 is complete, so these are both empty, which gives us a lot of information. And I guess there are our bridges. we can, I guess, extend said bridges. Although I think our final clue is probably the 5 that we have to work with. Because a 5 will see more than just one bridge. It sees 2 bridges, which is probably the blue bridge, the middle bridge, and the bottom bridge. Now I probably won't see the top bridge, because the top bridge, no matter how far down you go, can never reach this 5's area. So it must be from the middle bridge and the bottom bridge. Now I know the bottom bridge cannot take this path, because if it did, it can only go backwards from here and take up at most this path up here. The 5, because it sees 5 mines total, has to see, I think, 3 from one bridge and 2 from the other. Right? That's the only way to get 5. Yeah, because you have, in these 3 columns, you have 6 mines from both bridges. And if you are losing one, you're either losing one from the middle bridge or you're losing one from the bottom bridge. And so, you can't lose 2 from the bottom bridge because that just breaks 5. So this can't be a mine. Nice. Okay, well this 4 is very simple. There are 2 mines in these 4 cells, so these 2 are both mines. This mine must come from here, which is probably the bottom bridge. And this one has to come from the middle bridge. So we can further extend. And in fact, because we now know that this mine is lost from the 5, it must have its final mine be back in 5's range. So this is definitely a mine coming from here, meaning that's empty. Can I draw better? We also know that because one of these are mines, for this middle bridge, this is not. We can say with certainty that these are both non-mines. One of these are mines. Okay, the 4 is actually trivial. These are both mines. Oh, I didn't see that. It sees these 3 mines. I thought it only saw these 2. Ah, dang. Okay, well I guess it's a restart for us. Man. Okay, I can do this. I can do this. I don't remember what I did. We did something like this, we did this, and also this, and we did this and this, which implies this and that and this and this. Implies this, which means this and this. That implies that, which then we've proven that this happens, which then implied this and that, and therefore this. Okay. What? So confused. Anyway. Implied this, and now because of this, yeah, implies this, which implies a whole lot of stuff. And we've gotten that out of the way. Alright, there you go. I guess I'll just start drawing the bridges back again because I don't know why I'm doing this, but I think we have almost one bridge. We have 7/8 of one bridge. Same for the other one actually. We have 7/8 of the other bridge as well. Just don't know where the final mine is for both of them. I guess now it might be time to talk about this. Now can't be a mine because this, where does it go? It can't go this way. So this can't be a mine. I don't think this can be a mine because if it were, this would have to come out to this way. To this bridge. And in doing so, this two will be broken. We'll see 3 mines total. So this can't be a mine. 0 is very simple. And I guess we have the first bridge. First complete bridge. Oh, and now we have the second complete bridge. Yay. Gives us this and that. And the final 2 bridges are here. Sweet. Almost didn't even make it. But there you go. 3 bridges. That's pretty cool. Yeah, we spent quite a lot of time on that, especially because I lost once. But alright, let's keep going. Product and triplet. I feel like we've done this before. Have we not? I guess we haven't. Wow. Sure, I guess. Product triplet. Alright, triplet means that mines cannot form 3 in a row or column. Non-mines also cannot form 3 in a row or column. So you can have 3 empties in a row or column. In a row. Yeah. Product means that clues represent the product of distances to the nearest 2 mines. This one's pretty tough. But basically, if you take the distances between 2 mines and you multiply them, you get this number. So this 1, for example, must be 1 times 1. So that happens. This root 2 must be 1 times root 2. So you can only see one thing that's 1 away. Same for this one, which is a 1 times 1. And I don't know. But we have a lot of triplet to work with. All of these are basically triplets. That's a triplet. That's a triplet. Those are triplets. I won't see those. Yeah. Now we can find the other ones. Those are empty. That's empty. That's empty. That's a mine, therefore. Okay, just because there's a mine doesn't say anything about that, because you can have the further away mines can be tied. That's definitely a mine. That's all we can do. I think that might be all we can do. Alright, this 2 root 2 now can't be a 1 times 2 root 2 because there's already a mine that's 2 away. So at best it must be root 2 times 2 root 2. Root 2 times root 2. Now that's a mine. Okay. This is definitely a mine by triplet as well. I didn't see that. So that's a mine. This is very trivial. A lot of these are very trivial. Just hard to see. That's the problem. That's a mine. That's empty. I'm just waiting for an outlandish like 5 or like 6 root 2 to just show up somewhere to deduce the final mines. Either that or I'm just missing something very obvious. What could I be missing that's very obvious? It's probably just normal triplet. Maybe it's just 1, but we do know at least one of these are mines, but we don't know how many. It could be 1, it could be 2. Let's be at least 1 though. Does that make a difference? Does that do anything? I don't think so. I guess if this were empty, that breaks because you have to have a mine here for the 1. But also because of this 3 now you have to have a mine here, and that breaks. So this can't be, and this is a mine. Okay. Well, now if this was empty, it doesn't do anything. If this is a mine, that's empty, which doesn't do anything. If this is a mine, then this is empty, this is empty, this is empty. So a lot of things become empty. This is a mine. This is empty. It doesn't break. It doesn't even matter what this is anymore. This could be either. If this is a mine, that's empty. Doesn't change anything. Okay, it must be something I'm missing then. Some pretty obvious thing I'm missing. Maybe the mine count is useful now. To think about how many mines you can have. Like how many cells do we have? 11. I mean, you can... I guess you can only have 1 mine here, 1 mine here, and 1 mine there. There you go. So there has to be an empty cell here, an empty cell here, and an empty cell here. What does that mean? Because there are 11 cells and 8 mines remaining, there must be 3 empty cells only. Well, there must be 3 empty cells in each of these lines, right? And therefore everything else has to be a mine. Now we can do stuff. Very cool. Alright, so it was in fact Minecount that helped us with it all. But it's also a pencil puzzle, this one. Because every clue over here, these 6 clues are all that we needed to solve the puzzle. It was actually all. Everything else was question marks. So if I rolled it over again, only those 6 clues ever showed up. Plus all these empties, I guess. But that means there is no other information that you ever needed. Playing the puzzle would not have like revealed any new information for you to use. Alright, let's keep going. Horizontal modulo. Modulo modulo means that numbers are the mod 3 versions of themselves. So because this number is actually a 7, if you divide by 3, you get a remainder of 1. Therefore, it is a 1. This 0 is a 3. If you divide 3 by 3, you get a remainder of 0. So it is a 0. So now what this means for this 0, for example, it could be all empties, or it could be mines here, here, and here. This 1 definitely just means a 1, because it can't be anything higher, it can't be a 4. And a 1 in horizontal, which I actually didn't say, oh sorry. Horizontal means that every mine must have something adjacent to it horizontally. So it must have a horizontal partner, basically. If there were a mine there, it would need a horizontal partner, but then that breaks 1, so this can't be a mine. Same thing here. Yes. This 1 can technically be a 4, but in being a 4, will then break the 1 below it. So it can't be a 4. It is just a pure 1. And being a pure 1, can't have a mine there, because it will be isolated. 0. Well, 0 is... 0 could be a 3. If this has to be empty by a horizontal, right? A mine here would just be isolated by definition. Okay. Now 1, 0 does still your subtraction rules do still apply in Minesweeper, just not as consistently. But here we can say that 1 and 0 imply that this set of mines here must have a difference equal to the difference between these two mods. So this here has a difference, this here has a number of mine equal to 1 mod 3 minus 0 mod 3, which is 1. So it has 1 mine in it, basically. This 0 is probably no longer a 6, because if it were... yeah, then there's already 2 mines here, which fails. So this 0 is a 3. Because it can't be a 0, clearly. I don't know. This 0, if it were a 3... if it were a 3, you must have a mine in here. If it were a regular 0... well then now this is also empty, putting a mine there. So I guess in all cases there's a mine here and there isn't a mine there. That's fair. Now if this happened, you have a mine here and here. For this 0, because this 0 is not a 3. But if this happened, then these are both empty because 0 hits 3. That's interesting. I guess not very useful. This 2 is a pure 2. I guess what we saw from that previous example is that there's always one mine in one of these two cells, therefore there's always one mine in one of these two cells. You're gonna compare states now, I guess, which is... yeah, because there's one mine in one of these two cells, it can't be the one in the inside because it'll be isolated. So it has to be one on the outside, which must have a partner. So that happens. Yeah. This one is either 1 or 4. This checks out. Yeah. Although this one is not just a regular 1 because it only sees 3 mines. This 1 and this 2 by regular Minesweeper means that there's 1 mine in here. And this 2 has a 2 in it. So this can't be empty, because if it were, you have a mine here and a mine here for this 2, and that will break this mine. So there must be a mine there. Oh, I think I can see something. If this were a mine, this breaks. In fact, if this were a 4, it breaks. If it were 4, this would be empty, this would be a mine for the 2, and therefore this cell now sees 2 mines and therefore breaks. So this can't be a 4, it's just a 1. Cool. Now these are both empty by horizontal. 0 is just a pure 0, which means that these 2 are mines. This 2 is finished, so that's empty, therefore that's a mine which must have a partner. 0 is a 3 because it can't be as high as a 6. This one is it's a pure 1 because it can't be a 4. 0. This 1 must have a mine there. Oh, no, sorry, I already sees a mine. I didn't see that. Okay, well, my bad. Sorry. Let's be here. Which now means this. Which now means this. Because of this is this and this and this and this. Oh, that's a 5. I guess we knew that. Yeah. Alright, so this 0. Well, 0 could be a 0, could be a 3. But couldn't it be a 3? If it were a 3, then this line which has 1 mine in it is just broken. So it must just be a 0. So there you go. This one is a 4, so one of these are mines. Although we do know that horizontal, this has to extend out. So this one is complete. These are both empty by horizontal. This 0 sees... Well, it sees 4 so far, so it must be 6. Must see 6. Which means there are 2 mines here. What that implies is that there's always going to be at least 1 mine in these 2 cells. That 0, which sees a 1 mine, must therefore be a 3. So these are all mines. That's empty by horizontal. 2 is complete, so those are empty. That's empty by horizontal. 1 sees 1, could be a 4 or a 1. Does it do anything? Yes, it can't be a 1. Because we now notice that there's 9 mines remaining out of the 11 possible cells, and therefore you can only have 2 empties. A pure 1 here will make 3 empties, so that fails. So it must be a 4. 0 here. Well, it sees 4, so it must see 6, which means that there is 1 empty here. And there are 6 out of 7 mines. 6 out of 7 cells being mines, so the empty implies that all of these are mines. These must each have partners, which gives us all total. Final mine state. Mine count. There you go. Alright, I used a lot of random vocabulary there, but there you are. Alright, let's keep going. Connected area. Alright, area means that I'm not gonna explain that anymore. Connected, I don't think we've seen before. No, we have. We have seen connected before. Alright, yeah, I'm not bothering to explain anymore. Let's just go play the game. Alright, this 2 must have something coming out through here. Because even if it has something here, this can only have an area of 1 at maximum. Now, connected means that mines must form a rectangle, which is pretty interesting in terms of area. Like, I think this has to be a mine, right? Because if this was not, this mine over here must have an area of 6, which just breaks the 2. Yeah. I guess the 7 is interesting. The 7 must see something else. Because the 7, if it were just a mine area of 7, which has to be a rectangle, can really only fit an area of 7 by 1. Which would, in both axes, kill off another 1 that's near it. So it must see something else. I think it's possible to have mines that look like this. Yeah. But not necessarily likely. Another way is if you had something like this. But we can now therefore say that this 7 by 1 thing is not possible. It must be 1 by 6. The 6, it must be 1 plus 6. Right? Because a mine here can only have an area of 1. A mine here can't have an area bigger than 1 because it would then form a non-rectangular region. So have a maximum area of 1. Mine here and here would cause this to have an area of 5, which also breaks it. Sorry. Because an area of 5 can't be vertical, that just breaks. Can't be horizontal because that touches this mine. So there's exactly 1 mine in here, plus an area of 6. An area of 6 can't again see a mine, see an area horizontally or vertically. So it must see the next best option, which is 2 by 3. And 2 by 3 always has a mine here. A 2 by 3 here would break the 1. Here would break whatever mine is in here. So it must be a horizontal 2 by 3. So this happens. You then either have this or this. I think either cases would always force this to be empty. Sweet. Alright, now I guess we know that this can't be the upper version because that will break the 4, so it must be the lower one, which gives us all of that. Now this, by connected, has to escape out, so that's a mine. And this is empty. Okay, this 2... Well, actually... No, that might work. It's either this... which always forces this to be empty. Or it's this, which means this is empty. So this is always empty. I guess from the 1 we would have known that. Okay. There's always 1 there, so this form must see 3 elsewhere. Even if this was a mine, this can't escape out to see 1 more to make 3. So it must always see at least 1 more here. which could itself be just 3 in a row. Or it could do this and then C4 total. Yeah, that's fine. If it were 3 in a row, I guess it's also fine. Yeah, it's also fine. Is there some way to break it? If this happened, then clearly it has to be a 1 plus 3. No, not really. You could do... this would break it. Because then these would be empty and they were isolated. So I guess in this case, it has to look like this. Which doesn't yet break because, you know, you could just do a bunch of random connections. So yeah. How about this 4? It's probably just 2, right? If this happened, this would be empty, this would be empty. This would have to come out here, which already gives you an area of 4. But from here, anything can happen, so... nothing. I guess we could sort of, like, look at it. So let's take a look at the 2 options now. It's either this, or it's this. So in the first case, we figured out that this has to escape through here, giving you all of this. In the second case, this has to be empty. This has to be empty. This has to be a mine. This has to be empty. So that's our first connection. Not connection, but this is our first thing that changes. This now can't be a mine either, because if it were, you'd be forcing there to be this area to form a 3 in a row. An area of 3, which has to be 3 in a row. But doing that would connect to this, which breaks. So it's not it's also empty. This could be a mine though, because you could have a vertical 3 in a row. But I guess the 2 things that are common are these 2. And that works. Alright. The 5. How useful is that? Well, in a lot of cases, in the yellow case particularly, there's a mine there. Right? And in fact, if this were a mine, then we know this has to be a vertical area, which now breaks the 5, because the 5 can only see a maximum of 4. So in fact, we also know that this can't be a mine, which is also a 5 apparently. Anyway, this 5 must see a lot more. So much is 5, but we don't know. Now this can't be a mine by non-rectangular region. So it really depends on whether this is a mine or not. If it was, then there would have to be a mine there. If not, there will be no mine there. Yeah. Although, the 4 now, the red fails now, right? Yeah, the red fails because the red doesn't give this an area of 4. Only the yellow does. So I guess yellow has to be true. Alright, state comparison for the win. Alright, the 5 here and the 5 there. This is an area of 5, so this 5 already sees all that. This must be empty. 4 is an area of 2. This must be empty by non-rectangular region. So you have this. 4 is not complete. 7 must see something. And this something must be a 3 in a row because it must see 3 more. The only way you can do that is like this. Has to exit out somehow. We're not sure how. This must be a mine, because if it wasn't, you'd actually isolate this entire thing. So now this is 2 in a row. Could be 2 in a row, could be just an extra mine, like here. Now this form must see something up here, because if it didn't, you can only see a maximum area of 2. And now in fact, if this is a mine, that breaks even more. No, it doesn't actually. This works. Yeah, it does. If this happened... No, this also works. I guess what we can figure out is... if this is empty, you'd have this. But if this is a mine, then you'd have... I'm pretty sure this is always a mine. Yes? Oh, thank you. That's empty, therefore. This can't go all the way up here because that would isolate all the things here. In fact, if this was a mine, it just is guaranteed to be a 4 in a row now. Because you can't extend it to here, otherwise you hit an area of 5. So this can't happen. 4 in a row we already know is wrong. Okay. If this reached this way, how would this 5 work? This 5 needs to see 3 more. I mean, that's possible. If it saw 3 more, it would fit the mine count. If the 4 went this way though, this would also work. The 5 would need to see 1 more, which has to be here or there. I think this is always empty. Because in the case where it did this, how would it see 3? It couldn't see these 3 because that's non-rectangular. This has to be a mine. Oh, I could see these 3 though. I guess it could. But I guess interestingly enough, in this case, that fails, right? Because this has to escape out here somehow. Which now means that this is a mine. Yeah, so in every case this is always empty. Oh. And now, this being 2 plus 3 doesn't work. So we now know this has to happen. Cool. And because there's 1 mine here, this has to be empty. Well, I mean, we already know that by connected, this has to come out this way. Ah, what an interesting puzzle. An interesting puzzle. Very interesting use of area like several times in a row, actually. The deduction they made were all pretty scuffed, but they were right. Well, that was cool. Let's see if I can do one more. Segment liar. I don't feel like doing this one. Alright, we're calling it. End of video. Yeah, we did quite a bit, I think. I don't know how many we did. Like 3. But to be fair, those were 3 pretty tough puzzles. Or 4, I think. Or either way, I hope you enjoyed this video. I'll see you guys next time. Bye bye.